All right, what's up, my chemistry people? We're going to do some quick problems here. I promise they're short and sweet, and you should have a pretty solid understanding of these things from first year chem. As we look at the first two problems, it says when liquid ethanol, C2H6O, burns, it reacts with oxygen gas to produce carbon dioxide and water, and 1,368 kilojoules of heat. So just cluing us into the fact that now we're going to work on the thermo part of these chemical equations. So thermochemical equation here. It says use the thermochemical equation to calculate the energy change that occurs when 12.5 grams of ethanol burns in excess oxygen. Okay. Given some reactant here, talking excess other reactant. I'm already thinking stoichiometry. I'm already getting excited. Question 1 says, what is the energy change that occurs when 12.5 grams of ethanol burns? All right, well, as we take a look at this thermochemical equation, this enthalpy change is the amount of heat that is released in kilojoules for every 1 mole of ethanol that is burned. And so we are not given 1 mole of ethanol, we're given 12.5 grams of ethanol. And if I do a quick conversion here to moles, this value of 46.068, again, is coming from your periodic table. I'm going to then do a quick conversion from moles to kilojoules. In other words, just treat your enthalpy change as another reactant or product in the balanced chemical equation. And for every 1 mole of my C2H6O, my liquid ethanol here, I'm going to produce 1,368 kilojoules of heat. Now, as I solve this problem, everything's going to cancel out except for my kilojoules of heat. And when I solve that, I get negative 371 kilojoules as the amount of heat that's released when I burn 12.5 grams of ethanol. Now, let's take a moment, wrap our minds around this. 12.5 grams is less than 1 mole. So since I'm burning less than 1 mole, I should expect a enthalpy change that's less than the enthalpy change for burning that 1 mole. As I think about just how much, well, again, some good estimation skills here will help you out. 12.5 grams is roughly a quarter of a mole, and again, that's super rough, of ethanol, right? Because 4 times 12 is going to be 48. So like roughly a quarter, which means that I'm going to produce roughly a quarter of the heat that's released from burning 1 mole. And again, I'm just estimating here. If we used 1,400, then if we used 1,400 kilojoules, half of that would be 700 kilojoules, and then a quarter of that then is going to be 350. So we're pretty darn close. Again, use your estimation skills whenever you can. I know it's treacherous on the multiple choice to do that estimation, but please make sure that you're practicing that. And the last thing I want to say with this problem, just always a good idea to start boxing in your final answer to let the AP graders know, if it was a free response, what your final answer was. Just makes it easier on them, and anything you do to make it easier on the AP grader is going to make your score a lot better. I also wanted to make a quick note that you may also see this as 371 kilojoules released. And it's not a negative sign here. Sometimes you'll see it that way, but you've got to include what's happening with that heat. So you'll see it negative 371 kilojoules. That's easier than writing out released. And again, it just means that the heat has been released, but you could see it as a positive value, but then right after that indicating that that heat has been released. All right, moving on to question number 3. This one, again, looks scary. There's all this data, all these numbers. What are we going to do? We're going to work through this problem that has an equation on your formula chart, and I think you'll find that these are pretty easy, pretty straightforward to do. We're asked to figure out from the standard enthalpies of formation. And again, so these are the enthalpy changes for the formation of 1 mole of each of these substances from their elements. To calculate the enthalpy change for the reaction that's provided to us here. We are going to use this formula. Delta H is equal to the sum of the enthalpies of formation for your products minus the sum of the changes in enthalpy of formation for your reactants. And as we take a look, our products are here and our reactants are here. And so as we look at this and as we work through this, our enthalpy change for the reaction is going to be equal to 6 moles of the enthalpy of formation for that CO2, which is negative 393.5 kilojoules per mole. Do one of these. Plus the sum of 6 moles times the change in enthalpy of formation for water, which is negative 286 kilojoules per mole. Then we just need to sum together the enthalpies of formation for our products. As we take a look, we've got 2 moles of our C3H6, which has a enthalpy of formation of 20.9 kilojoules per mole. And then, oh man, we have another reactant here that is not listed in our convenient data table here. This is going to be something that's really common that occurs because this thing that's not listed is an element. And elements in their standard states have enthalpies of formation of 0. And so it's really important to recognize that anytime you've got an element, it could be a reactant, it could be a product. Anytime you've got an element in your equation there, its enthalpy of formation is going to be 0 kilojoules per mole. So although this is kind of not necessary, I'm just write 0 kilojoules per mole. And again, you'll probably get thrown off because you'll be looking for oxygen. You can't find it. Oh my gosh, I can't solve this problem. It's too difficult. No, it's just that it's 0 kilojoules per mole. So if we sum these together here, we're going to end up with an enthalpy of formation of our products to be negative 4,077 kilojoules minus a sum of our enthalpies of formation of reactants to be positive 41.8 kilojoules. And if we subtract those two, we end up with an enthalpy change for the reaction to be negative 4,119 kilojoules. Again, remember sig figs, I'm subtracting here, so I'm going to go to the measurement with the fewest digits to the right of the decimal, which is our enthalpy change for the products. There are no digits right of the decimal. So we're going to end up with an enthalpy change that looks like this. All right, and then the last thing to keep in mind is that you'll often be provided with these sort of energy diagrams for a reaction, thermochemical reaction, which we're sort of focused on what's going on with the transfer of heat energy. In this problem here, notice it looks a little bit different from the ones that we talked about in the notes. You've got this giant hump up here. What's that about? That, as we'll learn about activation energy in later units, right now all I want you to do when it comes to determine the enthalpy change based on these energy diagrams is recognize what the energy of your reactants are, what the energy of your products are, and then generally what you can do, again, although this is a little bit oversimplified based on the energy diagram, you want to use that formula where the enthalpy change is equal to the sum of the enthalpies of formation of your products minus the sum of your enthalpies of formation for your reactants. And so if we're trying to determine what the enthalpy change is, well, for our products, we get that enthalpy change to be 300 kilojoules. And for our reactants, we get that to be 250 kilojoules. So our change in enthalpy for this reaction is going to be a positive 50 kilojoules, which implies for me, based on the sign, that this is an endothermic reaction, or I've had to add essentially this 50 kilojoules worth of heat. Again, we'll talk activation energy, this little bump later. But essentially 50 kilojoules of heat was absorbed from the surroundings and taken into the system.